Hey everybody, it's me. I cannot be there today, but I still wanted to make sure that you got your information that I need to give to you. I need you to go to page 10 in your note packet, and when you get to page 10, we're going to start talking about the Coriolis effect. So you can just pause for a minute until everybody gets caught up. That would be great. Okay, so here's the video.
With a simple game of catch, I think I've found a way to show an effect that will have you doubting your very own eyes. Now, they don't know it yet, but our budding ball players sitting on our specially rigged merry-go-round are about to demonstrate a rather astonishing optical illusion. Right, here's the game, right? You're going to throw the ball straight to, what's your name, Victor, right? But this time, I'm going to complicate things slightly. I'm going to rotate the merry-go-round counterclockwise. So you throw it whilst it's moving. What's going to happen?
I don't know why, but I feel like if we're going fast enough,
Yeah.
like I might actually be the one catching the ball.
Okay, so you're going to throw it and you're going to catch it. All right.
Yeah, I don't know.
Right, what's going to happen, dude? Oh, it's going to veer off to the left. So the ball is going to swerve off to the left. Yep. And you might catch it. Possibly. Okay, good. Right, so what's going to happen?
I think it's just going to come straight to me, and I'm going to catch it like the champion that I am.
Show me the catch. Okay, great. Right, okay, so everyone, no, hang on, one more. Spencer.
He's not arrogant.
Just quietly
He's
confident.
not catching it. He's
Really?
not catching it. No.
So what's going to happen to the ball?
I'm catching it. It's right here.
Great, so we've got one saying to go off to you, one saying to come to you, Spencer, and you think it goes straight ahead, but you think you'll be the one catching it.
Yeah.
Now remember, the ball will be thrown straight across the spinning merry-go-round, but where will it end up? Will it be caught by the thrower? Will it be caught by the person opposite? Will it be caught by the person to the thrower's left? Or by the person to the thrower's right? Right, in your own time, throw the ball.
I got this. Oh!
So the answer was D. It was caught by the person on the thrower's right. Our camera angles seem to show the ball bend in the air. So is that a camera effect, or are we seeing what they saw? Hang on, this couldn't get much more simple. The idea was just to throw the ball straight to Victor to show us his amazing catching skills.
That's right.
Yeah, it did. It just curved right over this way.
So let me get this straight. So you threw the ball, it left your hands, and then what?
And then it just got sucked over to him.
In the air.
Yeah, I threw a perfect throw.
What did you see?
Yeah, curved right in.
Right, so we all agreeing here the ball curved in midair.
Yeah.
Yes.
And you didn't cheat this at all.
No, I didn't.
Okay. And do you know why it did that?
No.
No idea. It's called the Coriolis effect. And it's very simple. It's objects in motion appearing to be, it's an optical illusion, appearing to be deflected off their intended course. So what's actually happening here is you are throwing this ball. You can only throw a ball in a straight line. Can I clear that up straight away?
Yes.
Even though it appears in your eyes to be bending. So you throw the ball straight, it's still going straight, but the table is moving below you, and all of a sudden, look who's in front of that straight moving ball, and it looks like it's bent off to the right because you're still looking at the guy you were intending to throw it to, and that, ladies and gentlemen, is a Coriolis effect.
All right, so Coriolis effects. When we go into your notes, the Coriolis effect is going to, oops, what am I doing? Oh, too far. All right, so Coriolis effect is going to be an apparent motion. So down here, it's an apparent deflection. Okay, these are the two pictures in your notes. Coriolis effect is when we have winds, air currents. They're going to bend to the right in the northern hemisphere, and they're going to bend to the left in the southern hemisphere. All right, the key thing is that it's from the direction in which it is leaving, or where it was or from original motion. All right, direction from original motion. So for example, in this picture, I remember this is all the northern hemisphere up here. So I have my person at the North Pole. The expected path is that it would go straight down. All right, but since the Earth is rotating this direction, all right, and counterclockwise, its actual path would make it appear that it went here. Because remember, it's apparent deflection. All right, so as this ball is being moved, all right, this person here is technically moving this direction, so it appears to land here. All right, because by the time the ball got to this point, this part of South America is over here. So that's why this is the actual path that we say it takes. Also, over here, when we see pictures like this, okay, this is easy to see. If I start right here, and I wish I had a little thing to write with, but I don't right now. If I was to start right here, all right, I can see that this is a rightward deflection. When the arrow points the opposite direction, what I want you to do is you're going to take your paper and you're going to flip it upside down, all right, and you're going to put this part at your body, and then this is going to look rightward. It looks left now when we're looking at it this way, but if you actually take your paper, turn it upside down, this is a rightward deflection. All right, so this happens in the northern hemisphere. Tomorrow when I get there, I'm going to show you what happens when the deflection, goes east-west. All right, it's still rightward deflection, but I'm just going to have to show it to you because I can't write on the screen right now. Down here in the southern hemisphere, the deflection is to the left. So if I start right here from where it originated, I can see that this is a leftward deflection or apparent leftward deflection. And the same thing here, take your paper, turn it upside down so that this point right here is towards your body. This arrow does indeed go to the left, even though looking at it as weight is on the board, it appears to go right. So this here, you definitely have to make sure you memorize this. All right, because that is the fact that you'll just be asked to memorize, but then we're also going to ask you to do questions where you're going to have to apply that to a picture like this where we're going to have to draw some arrows, okay? Like I said, when I get back tomorrow, I'll go over this a little bit more, and then I have a demo that I can show you in class for the Coriolis effect. Another evidence for the Earth rotating is the apparent movement of celestial objects. All right, so the sun and other objects appear to move westward across the sky. All right, meaning they rise in the east, they set in the west. All right, and this is simply because the Earth is rotating. All right, and it goes from the west to the east, or we talk about counterclockwise. All right, so that counterclockwise rotation makes objects appear to move. All right, now for one of the coolest things that I love are star trails. So we're going to talk about how star trails can provide evidence that the Earth rotates. All right, so Earth rotates at a rate of 15 degrees per hour. So if I was there, I would ask you to remind me why that happens. If you go back on page 9, we did the why. All right, so NOPAC at page 9, we talked about why the Earth rotates 15 degrees per hour. And since we rotate 360 degrees in 24 hours, when you do 360 divided by 24, we're going to get 15. All right, so remember, this part here is one of those, you better make sure you memorize it. It's going to come up for this probably whole quarter. All right, so star trails. Star trails are going to make these circular paths around Polaris. All right, remember, Polaris does not move or does not appear to move because it's aligned with our North Pole. And just as a little review again, we use the pointer stars and the Big Dipper to locate Polaris. And Polaris is the first star on the handle of the Little Dipper. All right, just keep that in mind. All right, so let me show you some super cool things about star trails. Where's my pause button? Oh, let me go back a minute. Okay, so what they're saying here is that he made a time-lapse photo. All right, so he set up his camera and he took 1,262 pictures. All right, so it was set up on a tripod and his camera was set so that every 30 seconds it took a picture. All right, so keep that in mind. Every 30 seconds, this photographer took a picture, and in total, he took 1,262 images. So hopefully the lights are off when you're watching this, and then you can see here's, if you look at this, right here is the Big Dipper, right here. So that's the Big Dipper. All right, and that would make this Polaris right there. We see the lights coming on and off in the house. We can see where the moon is because we can see the shadows moving. Over here is Cassiopeia. Looks like the W. Alright, so right there, that would make that Polaris. That didn't move. Alright, so wait for it. He took all the pictures and he stacked them, so he piled them on top of each other. Alright, so that image that he took, these are called star trails. Alright, with the star trails right here, this was made by those stars making streaks, all right, as the Earth was rotating. Right here in the center, that would be Polaris. You're not going to really notice Polaris making a streak because Polaris doesn't move. All right, if we also notice, if we can take, you know, this here, all right, so maybe it's a little less than half a circle, right, because it's an if it was to go all the way around. So he took pictures for, you know, less than 12 hours, maybe 12 hours. If I look here, see like this path would have started over right here where my pointer is, went around. It would have started here, went around this way. The further out I go, it looks like that trail is longer, but I'm going to show you something in a minute. So we can actually take these star trails and we can measure the angle of, you know, how much distance that angle made, that arc, I guess you would say. And we can use the fact that Earth rotates at 15 degrees per hour to figure out how many hours this picture was taken for. And that's what we're going to do in a little bit. All right, but I have another video that shows you really cool star trails as well. All right, so this is a compilation of pictures taken in Nevada. This picture, you know, it's just what they give me, so they kind of ruined it. But right in here, that's like in this section right there, that's right where Polaris would have been. Here are cars up on a road, so that's what you're seeing there as the car drives by. Oh, here's the Milky Way galaxy, so that's that band of Milky Way stars. Alright, and this is the resulting still images. We saw them in like fast forward time lapse. So they're just, these are like one of my favorite things to look at. If you Google images, you get to see that it's evidence of Earth's rotation, which is just super cool. Alright. So these are images that, you know, I showed you those beautiful pictures. This is how we have to represent that on basically a test. All right. So what we have here is, you don't have this picture in your note packet right now. All right. So what we have here is that it shows going around 360 degrees. So being one rotation. And then it says star trail 1, 2, 3, 4, and 5. So we have 5 star trails here. And I remember when these were, oh, and 6. When this was taken, this all would have been from the same image. All right, so from a diagram like this, I can determine how long Earth was rotating. So if I look at